Okay, so thank you. So good morning, everyone. So I'm Alexis Horde Vo, and I'm going to present the project I want to pursue for this PhD, whose title is Identification of the Origin of Place Names via Geographic Information Retrieval. So my supervisors are Matakan and Estrita. So I'm going to give you a context to understand the problem behind the identification of the origin of place names. We can wander in the center of Melbourne and discovering streets that have names, buildings, and all these components have a name. For example, Little Bourke Street or other places, and we can wonder who is the person behind each place name and what is the history that is linked to these places. When we observe more clearly in the center, we can have a spatial correlation because all the streets have a spatial correlations and are all linked to the same types of persons who contributed to the construction of Melbourne. And more particularly, they are all males. So naming authorities, Geographic Names Victoria, came to us with one question, is to detect the gender behind each place name. And finally, it's a wider problem, and it's a problem that is linked to the enrichment of spatial databases of references that are gazetteers. Here, we only work with one attribute, which is the origin of place names. So just to give a small illustration, we have a very simple question. Who is Batman Street in Melbourne named after? And this is going to use three dimensions. First, information retrieval, where we are going to extract information from large databases in order to find an answer. We are going to have a perfect match with textual spatial data with Melbourne, and we're going to combine natural language processing with geographic artificial intelligence to disambiguate the origin of place names here with one word. And the objective is to find the exact origin for one place name, but sometimes it can be hard and not present in knowledge bases. And that is why we are going to recommend the most plausible candidates based at the same time on semantics and spatial matching. So to illustrate the work, we want to extract knowledge from documents. We have, for example, in green, we have potential candidates, Elizabeth II or Richard Bourke's wife, and we have also their impact, the impact that they have on different locations. All these locations we can organize in a knowledge graph in red, and we can inject other and external information, for example, containment, proximity, or other types of qualitative spatial relations. The idea is to disambiguate the documents as an input and to match the candidates to locations through relations in blue. And the final step is to detect is to make the prediction of the link that says that this person gives his name to this street. So finally, the significance of this project is to enrich incomplete databases. So we have three research questions. And the first one is more about the representation of spatial information. Traditionally, we have the image of geometries, but here we can see that with knowledge graphs, we can inject more relations, for example, containment, proximity, adjacency that can be useful for this task. Second research question is about automation. We can find the origin of place names through social science by reading books, but it's a very time-consuming task, and that is why we want to automate the process with language models. And finally, the third research question is to answer to give an answer to the initial query, is to identify the origin of place names. For the literature review, I decomposed into two parts. The first part is the representation of spatial information that can be used for information retrieval. And second, it's information retrieval in itself via question answering. So first, for the representation of spatial information, we can have pseudo-explicit representations. That means that they are readable by a human, for example, unstructured text, as we can have in Wikipedia archives, or we can have semi-structured tables that are traditionally used in geographic information systems, or we can have structured knowledge graphs that are a set of triplets with subject, relation, and object, as we previously showed before. But more recently, we have abstract representations called embeddings that store the representation of information through embedding. Capturing spatial information is associated with the idea of a footprint or locative support. Previous work tried to disambiguate or geolocate text by projecting the text and finding the exact match on the Earth through grids or kernel density estimators, but little work study the geolocating through knowledge graphs. That means linking a text with locations, nodes in the knowledge graph. We can see two main gaps. The first one is that spatial information is richer than crisp geometry. Crisp geometry that can be associated to one point or very simple point. We can have multiple geometries. And also the second gap is that the geometry of, for example, one country can vary throughout time depending on the boundaries of this object. For information retrieval in natural language processing or in geographic information retrieval, we always have the same process. It's one question and documents as inputs and different models. For example, an indexer to organize the documents to make faster queries, a ranker to match the question with the most relevant document. And more recently, we used generators, for example, in retrieval augmented generation, to generate answers based on multiple passages. For geographic information, we have one limitation in literature. The first one is that the rankers are mostly trained on general knowledge, but not on spatial knowledge. That means that these rankers are not specific to can't properly understand relations of proximity or make links between close elements. The second one, which is it's a limitation based on the nature of the documents. They are mainly unstructured and they can convey lots of ambiguity. That is why creating knowledge graphs via entity and relation extraction can be useful in order to disambiguate the text and to extract spatial information. To do so, there are two steps: is detecting the entities through named entity recognition and the creation of H's. And in this case, there are two subfields. Either we have a fixed set of relations, and it's, for example, a task of classification with supervised methods, or we can assume that we have an illimited number of relations, and that is why we are inside the domain of open relation extraction. Finally, for our literature review, we can see that language models are not sufficiently exposed to understand concept of space due of their training of general knowledge and not on spatial information. We can see that spatial information is not only a geometry, but we can have qualitative relations, containment, for example, or proximity that are not that is a rich that can be a rich component well manipulated in the knowledge graph, for example, and in the pipeline of information retrieval, the ranker is not the current rankers are not don't properly deal with spatial information. For the methodology, we can just model the problem as follows. We have a knowledge graph with vertices and edges. From these vertices, we can extract place names that we want to disambiguate and potentially their candidate's origin. The edges represent the relations. We can, in this graph, we have a subset. This knowledge graph is divided into triplets, triplets of X, a relation, and the candidate origin Y. And we apply two thresholds. So this is the problem statement for all the candidates in all the nodes in the knowledge graph. We want to predict for given a knowledge graph and a place name X, we want to predict if the triple X as for origin a given Y is existing. So we are going to calculate this probability and to have a threshold. That means that we are going to keep only the most meaningful candidate origins. And also in the second time, it's not only extracting an origin, it's also explaining. So it's about extracting a subknowledge graph that allows to see a similarity based on this subknowledge graph for the candidate origin and the place name to answer the question. Finally, for our methodology, I decomposed into 3 steps. The first step is only based on the use of text-based language models that are trained only with general knowledge. So we are going to use state-of-the-art models and to evaluate the performances in the pipeline of information retrieval with the different models. We're going to evaluate its understanding based on semantic and spatial similarities for our task. Also, we are going to fine-tune by injecting knowledge through the traditional paradigm of fine-tuning, and inject spatial knowledge inside this model and to see if they can provide good answers or not. Finally, we assume that it's not enough, and that is why we're going to extract, to find a new representation for knowledge and to extract spatial information. That is why we're going to have to define a corpus on which we want to find the candidate ends and the candidate origins. So we're going to create a knowledge graph from Wikipedia in the first step. We're going to define a knowledge graph based on toponyms, a spatial knowledge graph, and we're going to enrich this knowledge graph by injecting spatial relations. And finally, very interesting step is to refine the final knowledge graph by disambiguate as much as possible all the nodes by maybe clustering relations and reducing the number of relations in order to have a more easy to manipulate, easier graph to manipulate. And the final step is to focus just on the task on the prediction of the link between a place name and a potential origin. So we're going to predict the link and to produce a rationale. That means extracting a subknowledge graph that allows for a final user to understand why a place name can be named after such person. So for this PhD, I decomposed as follows: a literature review throughout the PhD. In the first year, it's mainly the first task as presented before. So it's the evaluation of current language models. For the second year and second milestone is the creation and the refinement of the knowledge graph. And the third year is to detect and to focus on the production of this link, as this rate as for origin this candidate. So now I'm going just to explain the first task we've done in the first year. So in the first year, we just used current language models that are at the state of the art in natural language processing for information retrieval. So we used Colbert. We injected Colbert in the general pipeline composed of a searcher in order to find relevant documents on the web. Here it was queries on DBpedia to extract subknowledge graphs as a base for our work. We used after Colbert that integrates both the indexer and the ranker, and we added a generator. And we had a very simple question, which is, who is Pattons Reed most likely named after in Melbourne, Victoria, Australia? Here we have three components. We have a semantic component in orange. It's linked to the origin of place names. And we have two other components that are related to spatial. We studied the relevance of the answers based on state level, for example, Victoria, and also we evaluate the relevance of the outputs based on the country level. And we're going to evaluate this on these three characteristics. The dataset used is provided by Geographic Names Victoria, where we have the place names and their origins. And we chose Melbourne because it has a rich historic background. So a lot of information on the internet. So we used this pipeline without fine-tuning and also with a fine-tuning. So for the fine-tuning, we just fine-tuned Colbert in the ranker with and Colbert finds similarities between a document and a question and the document. So to fine-tune, we inject spatial information by creating questions. For example, what is the country that is next to, for example, Australia? And we create a data set of questions, answers, just to fine-tune the model and to understand spatial similarities. And also we fine-tuned to the model to understand the format used behind knowledge graphs, which is the format RDF. Finally, we have 5 models. One model that is not fine-tuned, one model C1 that is only fine-tuned on to understand RDF, and 3 models that are fine-tuned to understand space. We observed that finally, for the semantic understanding, finding the origin of place names is still a hard task for the documents, the corpus we extracted. But what is more particular is that for geographic similarities, for Australia, we don't have 100% of answers that are related to Australia. And here, for answers that are related to Victoria, we only have less than 50%. That means that even if we inject this information in the question as a filter, for example, who is the street named after in Melbourne? The in Melbourne is not used, properly used in the language model. So it's still, we have still room for improvement. And as an interesting observation is that despite the low scores we have after the fine-tuning, maybe the fine-tuning allows just to limit the loss of information throughout the modular pipeline. Here, by fine-tuning with the spatial information, we have less loss of information, which is an interesting characteristic. So to conclude the work, language models are still insufficiently trained to understand spatial information, and just training helps to limit this loss in the sequential pipeline. This work is under review, so we published a book chapter to present this work with all the more analysis in the background and all the metrics. This is the article. So this is the project I want to pursue for this PhD, and I'm very happy to listen to your questions or precisions. Thank you.